that way? Sorry. Okay, so X was the number of trials to get a success. That's what a geometric model is. X is approximately geometric, determined by P, the probability of success. Now, this formula right here is the same. There's one just like it in your book. This is the probability that X equals X. So like in the last problem, the probability that X equals 3. The probability that X equals 3. It took me 3 times to get 5. Would be, it says Q. What's Q represent? Failure, the probability of a failure. What's the probability of a failure in the last problem? Probability of failure, 5/6, the last example that we did, okay? Rolling a 5 or not rolling a 5. So in the last example, if I want to know what's the probability that X equals 3, that it took 3 times to get a 5, I would take failure, the probability of failure, which is Q, or 5/6 to the X minus 1 power. Now notice this says X equals X, so what is X in my example that I'm doing right here? 3. So 3 minus 1, it gives you what power on the 5/6? 2 times P. What's P? 1/6, the probability of success. Is that what we did to find the probability that it took 3 rolls to get a 5? Did we take 5/6 times itself and then times 1/6? How would you know that? You look back on the previous page. Did we do that? What's the probability that I get my first 5 on the 3rd roll? That we did that? And didn't we take 5/6 times 5/6? Or 5/6 squared times 1/6? So we already worked this problem out. I was just showing you at the top of this page using the formula that they give you. This is the formula for finding any geometric probability. Memorize it. Okay? You don't even have to memorize it if you just remember, you know, putting blanks and filling in the success or failures, and the last one is always the success. Okay, so Q, it tells you Q is 1 minus P, or the probability of failure. Now, expected value. Do you remember learning about expected value? It's like the average. On average, how many times would I have to roll the die to get a 5? That's the type of question. That's what the expected value means. Instead of saying mu, you could write E of X. Mu is 1/P. So the expected value of a geometric model is 1/P. And the standard deviation of a geometric model, sigma, is the square root of Q divided by P squared. The square root of the probability of failure divided by the probability of success squared. And you will be asked to find these things. Okay, so this is the formula for finding a geometric probability. The probability that X equals 5 rolls to get a 5. The probability that X equals 10 rolls before I get a 5. Okay, and then you can find the expected value, or the average number of times you'd have to do something, and then the standard deviation. So we want to look at another example now, and we're going to use formulas. So there's just a little note here. It's not a necessary note. If you've taken pre-calc, you might remember it, but if not, don't worry about it at all. This is called the geometric distribution, since probabilities form an infinite geometric series with a sum of 1. So that's nice to know information. Not need to know. So suppose that 30% of certain high schools students have a driver's license. On average, how many students will you need to randomly select to find one with a driver's license? All right, so first thing I'm going to do here is I'm going to decide, is this actually geometric? Is this geometric? First I'm going to decide, is this Bernoulli? Bernoulli, yes or no? So first of all, what are the 2 outcomes? Okay, they have a driver's license or no driver's license. Okay, good. So 2, probability of success, P. Probability of success is always the same. What's the probability of success here? What's the probability of having a driver's license? 30%, 0.3. They tell you that 30% have their driver's license. We know that for a fact. Okay. And then third, are they independent? Now this is one of those cases where technically if you're going to ask students, you're taking people out of the population, but if you're only asking like 8 people out of a whole high school, is that really going to make a dent in their population? It actually goes back to this rule right here. Note, whenever we sample without replacement, do you suppose you're going to have to ask 150 students before you find one that has a driver's license? No, probably not. So I would say that yes, it's going to be independent. We will ask less than 10% of all in high school. Okay. So again, that goes back to that rule on the first page under number 3. Okay, so it's Bernoulli, we know that. So now is it geometric? So are we asked how many we're going to have to ask before we find one with a driver's license? Is that what? How many students will you need to randomly select to find one with a driver's license? Aren't they asking us that? So we're just going to keep. So this is geometric, so we can say X is geometric. And what is the probability of success? What is P? What's the probability they have a driver's license? We already answered that once. 30%. So X is geometric and the probability of success is 30%. Okay, so now we can answer the question that they asked. It says, how many students will you need to randomly select to find one with a driver's license? Now here's the key word. The key word here is on average. Okay, if it says on average or how many students will you expect, this is asking for the mean, the expected value. Whenever a question says on average, and they ask this a ton here, they're asking you to just find the expected value. So what's the formula for the expected value for the geometric model? 1 over P, and P was 0.3, so 1 divided by 0.3 is 3 1/3. Or 3.3 repeating, but 3 1/3 is a nicer way to write 3.3 repeating. And so I would, so 3 1/3 people. So you should write this down. I expect to have to ask 3 1/3 students before I find one with a driver's license. I expect to have to ask 3 1/3 students before I find one with a driver's license. That's the interpretation of the expected value or the mean here. All right, so now we want to know what is the probability that we'll take less students than expected. Okay, so what is the probability that we'll take less students than expected? Well, how many students did I expect to ask? 3 1/3. So less than that would be the probability that X is less than 3 1/3. Now pay close attention to this because my formula, does my formula include a less than sign? Yes or no? No. So this is not something I can find by just using that formula one time. It's not that hard to figure out, but you have to do more than one probability. So to find the probability that you have to ask less than the expected number of people was 3 1/3, this means the same as the probability that I have to ask exactly 3, or, which is also plus, remember or probabilities get added, or plus the probability that I have to ask exactly 2, or plus the probability I have to ask exactly 1 person before I find someone with a driver's license. So a less than probability or a greater than probability in dealing with geometric, you have to rewrite it as every number below that with the equal to, because the formula only works for the equal to. So now I have to calculate what's the probability that I had to ask exactly 3 people. So here's my formula. The probability that X equals X is equal to Q to the X minus 1 power times P. That's the formula from up above. So the probability that I had to ask exactly 3 people, remember this is the first 2 people say, nope, I don't have a driver's license, and then the third person says yes. That's what this formula is going to calculate. So that'll be Q. What's Q again? Probability of failure. What was the probability of failure here? If the probability of success is 0.3. 0.7 raised to the, how many people are going to say no if I ask 3 people? 2 of them to the second power times the probability of success, or 0.3. That's always the last one. It's only there once. The probability of success is just there one time because the last person says yes and then you quit. Okay, plus, now the other scenario is I only had to ask 2 people. So the first person says what? Nope, 0.7. That's their probability. They say, nope, I don't have a driver's license. The probability of that happening was 0.7. The second person says yes, 0.3. Or plus, okay, what's the probability that the first person I ask says they have a driver's license? I ask them, they say yes. What was that probability? 0.3. It's that simple. First person said yes, 0.3. So now I multiply these, add all of these together. Does anyone have it? 0.657. Okay, so the probability that you have to ask fewer people than expected is 0.657. All right, now the next question is, what is the probability that it will take more students than expected? Well, isn't that just the probability that x is greater than 3 1/3? So wouldn't that be like the probability that x equals 4 plus the probability that x equals 5? What's going to be wrong with this? You can go on forever. You can go on until you've asked every single person in the school. We don't happen to know exactly how many people are in the school. And this would be kind of a giant pain, don't you think? Is there an easier way or another way that we could figure this out? How are these two things related? What would these two probabilities have to add up to? 1. Wouldn't they have to add up to 1? Asking fewer people than expected, more people than expected, don't they have to add up to 1? So isn't this the same as the complement of that one? Couldn't I figure this by taking 1 minus the probability that x is less than 3 1/3? And didn't we already figure that out? What was the answer to that? 0.657. We just figured it out right up above. So 1 minus 0.657 is 0.343. So a lot of times if you're asked a greater than question, it's usually the complement of the less than question. So. All right, so for your reading, you, like I said, have 5 pages to read about the geometric model, and you have 5 homework problems. Number 2 is the one that asks you to decide if it's a Bernoulli trial or not. And the way you decide that is it's just asking about Bernoulli. You go up here and look at and clarify 1, 2, and 3. We did it twice in our notes too. So before you actually start your homework, I have a couple problems that I want you to look at. And basically it's just problems 1 and 2 here that I want you to look at. And, you know, just maybe do them at the bottom margin. If you want to work with a partner, that's fine. But I just want you to answer the questions 1 and 2 right now while Bernoulli and geometric are fresh on your mind. Just try to answer these 2 questions and we'll go over them in about 5 minutes. So.